Today we're going to talk about the hydrostatic balance and really get a better perception of what buoyancy actually is. Now, it's important for you to remember that things in the atmosphere, things anywhere in the universe, move or at least change their motion because of something we call a force. So everything that we do is about having a force that causes a change in the motion. So with all of meteorology, with all of physics, with all of the universe, we care about forces. Okay, so we're going to talk about important forces that cause the air to rise. Now, I'm going to start over here. I'm going to share my screen. So if you don't mind, I will move this here, share the screen. There we go. And in sharing the screen, I'm going to put a little box. Now we've dealt with this parcel. We know all about it. Now, if you remember what we said buoyancy is the fact this parcel is less dense inside, is less dense than the density outside. We know that the pressure is the same both inside and outside. And this is important. Whoa, that's not a straight line. This is a straight line. That's an important fact, that the pressure is the weight of the air above you. So both inside the parcel and outside the parcel, there's air. And that air is got weight and it's pushing down equally. So what that means is we say that the pressure inside the parcel is equal to the pressure outside the parcel. So rho is density, P is pressure. And when the pressure is the same both in and out, the reason it's less dense is because in this case, the temperature inside is greater than the temperature outside. So that there's an inversely proportional relationship between temperature and density when the pressure is the same. And that would be something I think you should write down. Go back, stop the video, write that down. In other words, if this box is less dense than the air outside, it's less dense because it's warmer. Warm air is less dense than cold air when it's at the same pressure. And that last part of what I just said is super important. Warm air is less dense than cold air when it's at the same pressure. Warm air is not always less dense than cold air, so I want to take a look at an example of when that would be. So over here, imagine that I have a parcel and it's down here by the ground. Lots of pressure, lots of air above me. Then I have a parcel up here. Now, typically in the atmosphere, not always, but typically it's colder up here. So let's just say this is cold air and this is warm air. Well, I thought you said warm air is less dense than cold air. But that's only true if the pressure were the same. In reality, the pressure down here is much higher than the pressure where it's lower. Okay? High pressure, lower pressure. So that there's a difference in pressure as we go higher up in the atmosphere. That difference in pressure as we go up can also impact the density. Higher pressure is going to push more effort, more impact on the parcel and make the parcel smaller, more dense. And if it's less pressure, it expands less dense. So the relationship between temperature and density being inversely proportional only matters if the pressure is the same. So for what I'm talking about, it's inside versus outside, not up and down. All three things are different, and there's a compensation going on. Okay, now let's go and try this again. I'm going to redraw my box, and I'm going to say, okay, look, let's take a look at forces acting on the box. Now, the very first force is what we call the pressure gradient force, the PGF, pressure gradient force. Now remember, a gradient is a change of something over a distance. And in this case, that distance is vertical. So that pressure gradient force is the change in the pressure over a vertical distance, which would be delta Z. How does the pressure change as you go higher? We could also write it dp dz as being this pressure gradient. Air wants to travel from higher pressure to lower pressure. So that means air naturally wants to go up. That's what the force of the pressure gradient force is trying to do. It's to push it upward. But there is also a force acting to pull things down. And I think that's pretty obvious. That downward force is gravity. So gravity acts downward. Now, to be more specific, gravity is an acceleration. According to Newton's second law, we need a mass times an acceleration to get a force. So really what I'm saying is that weight is mass times gravity. That's what we define weight to be. So I need a mass term in here to make it true, because acceleration and gravity are the same thing. So gravity is an acceleration, at least the way that we're doing it here. So I need to multiply by gravity. I need to multiply by mass. The only thing is, how do I have mass? Depends on the volume size. Doesn't it? Big volumes will have more mass. What if I multiplied by density times gravity? Okay, density is mass over volume. So really what I want to say is, yes, I need mass, but that mass is density. It's the mass of the volume. So I want you to think about density being the mass of this volume. Okay, remember this is three-dimensional volume. The box in reality is a cube. Okay, so gravity is going down, pressure gradient force, air wants to go up. They're going in opposite directions. So the way that we normally would write this equation is dp dz is equal to negative rho times g. And that's what we're looking at, negative rho g. This equation is called hydrostatic. That's the name of this equation, the hydrostatic equation. And you could have written it, change in pressure over the change in height is equal to minus rho g. The hydrostatic is the fact that the pressure gradient that says the air wants to go up, move from high pressure near the ground to lower pressure up, is balanced by the weight of the air down, which is gravity. Okay? Now, there are times where this equation is written differently. I divide both sides through by density. So it may look like this. G. And so another way to look at that is we can say that this negative 1 over rho dp dz is the pressure gradient force, or the acceleration from the pressure gradient force that's balanced by gravity. Does the negative sign have to go on this side than this side? No. The negative sign, pretty honestly, if you remember that they're just going in different directions, doesn't really matter for our use in class. Do I have to put 1 over rho for this? No, you could do it like this. Both of them are correct. They're the same thing. But I'm going to do this, and I'll keep it this way for a reason. So now I'm going to go in here, and I'm going to say, okay, look. I'm going to erase this for a second, and I'm going to say, I have got a force going downward balanced by the force going upward. So the upward or the downward force is gravity or if you are a stickler for semantics, making words right, you would actually probably want to say weight. And then this is the vertical pressure gradient force. So if I asked you on a test, hint, hint, what is the hydrostatic? You would say it's the balance between an upward directed vertical pressure gradient force. In other words, air wants to go from high pressure down low to lower pressure up, is balanced by gravity, or is balanced by weight, which is pulling it down toward the center of the earth. This balance is really important. This balance is really strong. It's really balanced, which means what's the net force? When these two are added together, I get no force. So this parcel has no force acting on it, and it wants to stay there. So when I go, hey, the air up there in the sky why doesn't it fall? See, I'm really playing the role of Chicken Little. Why doesn't the sky fall? And the answer is because the air that's up there has a force and a desire to come down, but there's also a force of expansion of the atmosphere wanting it to go up, and those things are balanced. So how does that balance get offset? Well, the balance is going to get offset is if this parcel, the way that we describe a parcel, a collection of air, is different inside from outside. If things are different, so let's look at this for a second. Let's imagine that it is colder inside, which means it's more dense than the air around it. Always outside of this, it's not up and down. This is comparing the pressure horizontally. By the way, we will find that we can make air move horizontally if we have a horizontal pressure gradient force. That's how we get air to move and the wind. This is vertical. So if it's colder in this parcel and more dense, then this parcel does what? Well, let's take a look at it. First of all, the thing that we want to make sure you understand is that there is, above this parcel, there's weight. And above the air outside in the darker green, let's get an arrow, there is also weight of the air. And since we're at the same location in the atmosphere, in and out of the parcel, we have the same weight of the air above you. So basically what we're saying is that the change in the pressure, this thing over here in the circle, with height, is the same both in and out of the box. We know there's gravity pulling down, and gravity is the same. So the only thing that can be different is the density. The density is the only thing in and out that is different. Since we said the box is more dense, what that means with the box being more dense is that this number becomes bigger. But if it's bigger, what does the rest of the box do? So you're making the denominator bigger, which means that the value of the fraction, or this, what's in the yellow box, is smaller. The upward force is smaller because it's more dense for the parcel than the air out here. So what we're really saying is that by making it colder, what we're going to do is we are going to say this upward force is now smaller up than outside, which means the downward force of gravity is going to win. It's not balancing gravity, which means what will the parcel do? And the answer is the parcel starts to sink. If it's colder, it's more dense. And more dense air in the environment that it's in will come down. But the reality is the downward parcel movement is because the upward force, vertical pressure gradient force, is going to be less. Gravity wins. You could look at it in this equation. You could also look at it in this equation in gray. There's an upward pressure gradient, that's the same, but the density is more, so in this parcel being more dense, it's going to come down. Saying the same thing, different ways to express it. And it might matter in the future if you study meteorology to think about that. But the idea is air will move on its own when there's an imbalance of forces. Cold air is going to sink. Okay, now let's go back for a second and what happens if it's warmer. So I'm going to see if I can draw this arrow back. Okay. And now instead of being more dense and colder, let me get rid of this. I'm going to make it warmer in the box and less dense. If it's less dense, then the upward force over here, which is in the yellow box, becomes bigger. And so this upward force, and here, I want to make sure I'm looking at this going, I don't want you to be confused. This is the weight, not of the parcel, but of the air above you. But because there's a density term into it, and it's warmer, it becomes a bigger upward force. So now instead of just being this, it is now going to be all this. It's a bigger force. It is not balanced with gravity. So there's an upward net force. And that means what will this parcel do? The parcel rises. Because it's less dense, makes an upward pressure gradient force bigger. An instructor, a mentor of mine, once asked, well, how does the parcel know it's warmer than outside? Doesn't have to. It looks straight up and it sees a bigger pressure gradient, and therefore it will ascend. It ascends by itself, and that's unstable. So buoyant air is unstable. And unstable air and buoyant air rises by itself. If it rises by itself, then we know there must be a force. And the reason there's a force is because the upward pressure gradient is bigger than the downward pull of gravity. And air rises by itself. Now, the last thing that I want to talk about is that what happens when I have air rising. Remember, we said force is equal to mass times acceleration. If there's a net upward force, that means my parcel is going to do what? It means my parcel is going to rise by itself, but there's a force, so it also means it's going to accelerate. And acceleration using vectors is going to be an arrow going up and then an arrow going up that's even faster. That is a vertical acceleration. As a result, and this is super important to always remember, unstable air accelerates. Unstable air accelerates. So if the air in an updraft of a thunderstorm is unstable, air is accelerating. If the air in the downdraft is unstable, it's colder, but cold air means there's a net force downward, which means it is unstable downward. That's an important factor. How fast will the air rise? How fast will the air sink? The faster the air rises, the stronger the updraft. The faster the air sinks, eventually the air spreads out, the stronger the winds. So unstable air accelerates. Let me get back to where you guys are. There we go. And that's the discussion on the hydrostatic balance and how the hydrostatic imbalance leads to acceleration of air. Buoyancy is actually a force causing the air to go up. It's an actual imbalance of two bigger forces, pressure gradient up, gravity down. And that imbalance creates a net force that causes air to accelerate. Okay? That's the way that we look at the atmosphere. Unstable air accelerates up. Unstable air can accelerate downward, which we'll talk about later on. But the key thing here is that unstable air accelerates up, and that's what instability is. So if you look at a definition of the term hydrostatic, most of the time you'll see that the hydrostatic balance is extremely strong in almost all of the atmosphere, except in one thing. And that one thing is convection, thunderstorms. So yay for thunderstorms. Thunderstorms cause acceleration of the air, and thunderstorms are really, really important. And I think they're kind of cool. Okay, and with that said, I'm going to find my cursor and I'm going to say goodbye. We'll see you next time.